Okay, so hi. In this video, today I'm going to present to you another branch of mathematics. This is calculus, and specifically in college, you will call this calculus 1. So the title for this calculus 1 of ours is differential calculus. Okay, the first part of usually the three-part calculus courses that you need to take up for college. So we have calculus 1, differential calculus, calculus 2, integral calculus, and calculus 3, differential equations. So this is the very first lesson for calculus 1. So this is the limit of a function. Okay, so for the limit of the function, there are some prerequisites that we are, of course, in our minds. You should finish at least algebra, intermediate, or better if advanced algebra. You should have know-hows in geometry, and of course um, some ideas about trigonometry. So the limit of a function. So let's go to the meaning of calculus first. So when you say calculus, it's a branch of mathematics that deals with the rate of change. Okay, branch of mathematics that deals with the rate of change. It literally means a small stone used for counting. Okay, so it is a branch of mathematics that study how things change, or say the rate of how things change. Okay. Um, Next is it was invented in 17th century by, of course, there is still dispute until now of who discovered calculus. So there are some treaties or a truce, shall we say, that it was discovered both by Sir Isaac Newton and Gottfried Wilhelm Leibniz. Okay, so I believe that Newton started with differentiation first in his work with fluxions, and Leibniz is the one who started with integration first. But of course, in our fundamental theorem in calculus, that both are of opposite operations with each other. So Leibniz is the one who used or created the integral sign. I don't know if I can make it correct. Okay, so it has two fundamental operations. Like I said, it is differentiation and integration. So for now, we're going to solely focus on one operation, that is integration, in this batch of videos. And these are all based on the concept of the limit of a function. Okay, the concept of a limit of a function. That's why it's much important to know the concept of the limit of a function, because well, it uses it makes use of it is around. Okay, it is part in the differentiation and integration also. Okay, now what are we going to do today, especially in this video? You should be able to illustrate the limit of a function using a table of values and the graph of a function, and you must be able to distinguish when we say the limit of a function versus if you're going to substitute it on the function itself. Again, distinguish between the limit of a function versus the one when you will just plug in and substitute it directly on the function itself. Okay, so moving on. So what is the limit of a function? So intuitively, the limit of a function f of x, this is our function, as x approaches something, let's say a value a. Okay, in symbols we write it as x approaches, as an arrow pointing to the right, approaches a, is the value that f of x as gets closer and closer and closer to a. Okay, so to illustrate that, let's have one example. Example 1. So given we have this function f of x equals x squared plus 1, say x squared plus 1. What is the limit as x gets closer and closer to 3? We can write this as x gets closer and closer to 3. Now, how do we do this? First, we're going to present it using the table of values. Okay, f of x gets closer and closer to 10 as x gets closer and closer to 3. How do we know that? Let's try to substitute using the table of values. So let's make it as x and f of x. First, let's try to know the values before 3. So the values before 3 are like, 1, 2, 2.5, 2.9, and so on until it will eventually reach the value 3. Okay, let's start with 2. So substitute, if x is 2, so what is f of 2? f of 2 is equal to 2 squared plus 1. That's going to give us 4 plus 1. That's going to give us 5. So that's 5 here there. Next, how about if it is 2.5? So 2.5, the same process is being done here. So you just need to substitute. That becomes 7.25. If it is 2.9, that's 9.41. Same process. If it is 2.99, 9.401, and so on. Okay, as you can see, it gets closer and closer and closer to the value 10. Okay, next up, um, how about if we're going to start with a number greater than 3? That is, we're going to start with 4, and then 3.5, and then going down and nearer to 3. So what will be the process? So 4, again, we're still going to substitute it here. So we have f of 4, oh, sorry, f of 4 equals 4 squared plus 1. That's 16 plus 1. That's 17. Okay, and then we'll continue this process with the 3.5. We're getting smaller because we need to get closer and closer to 3, remember? So we need to get smaller if we're going to start with 4, and we need to get bigger if we will be starting with 2. So 3.1, 3.01, 3.001. As you can see, this approaches some number. As you can see, that this becomes 10, and then 10.06, and then 10.006, then 10.000 something, and eventually it will also approach 10. Okay, now from here we can see that the limit, therefore we can say that the limit of f of x as x approaches 3 is 10. In symbols, this is how we write it there. So how do we read this? The limit of x squared plus 1, better to use the parentheses so that we will be careful with that. The limit of x squared plus 1 as x approaches 3 is equal to 10. Okay, so that's our concept of the limit as a number, as an x, as one x approaches one number. What is the number that it is both approaching it from the left and the right? Okay, next up, what example number 2? So how about if we're just given the graph, not the equation of the function itself, the graph of the function. Suppose we want to find the limit of this function, f of x equals x squared minus 2x as x approaches 1. So where's 1 in our x-axis? Here it is. This 1. So we need to look at the values of x as it approaches from the left and from the right. Okay, so as we can see, as we go on and on, as we approach 1, we go to a certain limit, that is this value here. And this value is -1 in the y-axis. Now, let's try to verify if this is also true for approaching from the right. So from the right, we will be tracing the function, the graph, and then eventually we'll still be ending at the same spot as the from the left. So this is still -1. So therefore, by the graph, by the visuals on the graph, we can say that the limit of x squared minus 2x as x approaches +1 in the x-axis is -1 or -1. Here you go here. Okay. Moving on. In general, to give it a definition now, the limit of f of x as x approaches some number a is written in symbols as this. So the limit of this f of x, this f of x must be an expression. Okay, it is usually an expression. As x approaches this a is, we read it as this, we write it as this. Okay, just take note that this um, limit of f of x as x approaches a is not really the same when we're just substituting it to f of a. You may be, tempted to say that it's just substitution because, if you're going to substitute it here in this example, so what is f of 1? So what is f of 1? So we have 1 squared minus 2 times 1. So we have 1 squared is 1. This is minus 2, this becomes minus 1, right? Also with the same with the same concept as the example before. So you may be tempted that, they are just equal when we say that we are substituting it with the a itself. Okay, but unfortunately it's not. Okay, it's not. Okay, substituting the value of a to the function is not the same entirely when we are getting its limit. When we are getting its limit. Okay, so let me show you why. Okay, so limit of f of x as x approaches a versus the f of a. So consider this function here. So we have f of x equals x squared minus 1 all over x minus 1. Now let's try to differentiate if we're going to get the limit versus we're going to get the um we're going to substitute the value in the function itself. So let's try to find the limit of this as x approaches 1. So what is its limit? Okay, so again, you may be tempted to say, whoa, maybe we can just, maybe we can just substitute it. Okay, but let's try to use our table of values, shall we? So we have the x, and we'll try to, this will be approaching from the left. Oops. Okay, and this will be our f of x. How about let's use 3 values here. So since our limit is 1, let's start with, sorry, let's start with 0, 0, let's 0 0.5, and then 0 0.9. Okay, now what is 0 if this is the case? So this becomes 0, this becomes 0, so you have minus 1 over minus 1, that's going to become 1. Okay, what's 0.5? So 0.5 squared minus 1, I need to have the calculator there. So 0.5 squared minus 1 is equal to 0 0.75. Okay, all over zero point 0.5 minus 1 is negative 0.5. Okay, and negative, I think this should be negative. So this will become negative 0.75 divided by negative zero point 0.5. So the answer is 1.5. Okay, so the answer here is 1.5. And then we'll try to use the 0.9 now, which is nearest, the one nearest with 1. So if we're going to apply that, so we have 0.9 squared minus 1. The numerator is negative 0.19, and the denominator is zero point 0.9 minus 1. That's going to give us negative 0.1, and divide them. Negative 0.19 divided by negative zero point 0.1. The answer is 1.9. Positive 1.9. Oops. Okay. Anyways, I think this is positive 1.5, not negative 1.5. So this is 1.9. 1.9. So I think clearly we can see here that this from the left, it is approaching some number, and I bet that's 2. Okay, I bet that is 2. How about from the right? Well, let's make another table for it. Let's just make use of 3 values. Okay, and let's start with 2, shall we? Well, let's try 1.5, and then let's try 1.1. Okay, which is the same with here. So if it's 2, so this becomes 2 squared, this becomes 4, 4 minus 1 is equal to 3. This becomes 2 minus 1, that becomes over 1, so this is 3. Okay, so this becomes 3. How about 1.5? 1.5 squared minus 1, 1.5 squared minus 1 is going to give us 1.25. 1.25 all over 1.5 minus 1 is point, sorry, zero point 0.5. So 1.25 divided by zero point 0.5 is going to give us 2.5. Okay, 2.5. And lastly, 1.1. Let's try 1.1. 1.1 squared minus 1 is going to give us 0 0.21 all over 1.1 minus 1 is 0 0.1. 0 0.1. And then let's put that 0 0.21 divided by zero point 0.1. The answer is 2.1. 2.1. So from here, I think we can conclude that the limit of this is approaching 2, as you can see. This is also approaching 2. Okay, getting closer and closer to 2, closer and closer to 2. So we can say that the limit of this x squared minus 1 as x squared minus 1 all over x minus 1 as x approaches the value 1 is equal to 2. Okay, so the limit is equal to 2. So maybe we can just put here equal to 2. But now let's try to see if we're going to substitute it directly in our limits value here. So if we're going to substitute it directly, okay, what will be the answer? By substituting it directly, so what we can see is we have what is f of 1. So f of 1 is equal to 1 squared minus 1 all over 1 minus 1. Therefore, what we can see is 1 minus 1, that's 0. 1 minus 1 is 0. So this is um, not a good number to look at. So 0 over 0, to tell you in advance, is what we call the indeterminate form. Okay, indeterminate form. We're going to discuss this in the future lessons, but for now we can see that at least we can see that the denominator is 0. So if the denominator is 0, that's not acceptable anywhere in the mathematics that we are talking about. So we cannot have a denominator of 0, and then making the denominator and numerator 0 makes it worse. So meaning we can see that if we're going to substitute it directly, this is not the same when we're just getting the limit. Okay, so therefore therefore, the limit of f of x as x approaches a is not equal to f of a. Again, this is 2. And if we're going to substitute it, f of 1 is 0 over 0. So meaning they're not equal. They're not equal. Okay? And if we want to check and verify using the graph of this function, what you can see is something like this. I've made use of one graphing calculator, and you can see that in the one in the ordered pair 1 2, there is a hole, meaning there is a gap in that line, meaning if we're going to substitute 1 here, that's going to be a hole. But then as you can see, if we're going from the left, going this to this point here, it approaches that number. This number is 2. Okay, if we're going from the right, it also approaches one number, that is also 2. Okay, so meaning the limit, okay, we have shown here that the limit is really not equal when we say we're just substituting. Okay, so we're just substituting, so meaning this is indeed true. Okay, because these things exist. Okay, so I hope I made it clear. You can rewatch this part if you want to, you want it to be clarified in your head. Now let's end this with the concept of one-sided limits. Maybe you can see that I am doing the limits going from the left, going from the right. Why am I doing that? Because of this. So in order to be able to say that the limit of f of x as x approaches a number L, we call that limit L, okay, exists, the f of x, the function values must approach L when x approaches a from both the left and the right. Again, so that the limit exists, meaning the function must approach the same value a from both left and right and must have the same exact limit value. Okay, so to give you one example, consider this piecewise function. So you know piecewise functions, right? Functions which are separated and then they have different domains. So you have 2x plus 1 for all x's less than 2. And you have x squared for all x's greater than or equal to 2. So if you want to get the value, the limit of this f of x as x approaches 2, so we need to find the values of x as x approaches 2 from the left and from the right. So let's start with the f of x, and let's start with from the left. So we'll start with 1 since we want to get as close and close to 2. So if 1 is substituted here, so we're going to substitute it in this function because 1 is clearly less than 2. So we need to substitute it here in this function there. And substituting 1 here, so we have 2 times 1 is 2, 2 plus 1 is 3. Indeed, that's correct. Okay, and then clearly we are going to get closer and closer to the value 2, and then voila, 1.5 becomes 4. Okay, 1.5 times 2 is 3 plus 1, 4. Um, Next is 1.9, it becomes 4.9. 1.99, it becomes 4.98. I think clearly you can see the limit here. The limit of this function is 5. Clearly, it becomes 5. 4.99999, that becomes 5. Okay, how about from the right? So if it's from the right, we're going to start with 3, correct? 3. And since it's 3, and we know 3 is greater than 2, so therefore we're going to make use of this function. Okay? So just square it. 3 squared is 9. 2.5, we're going to approach 2, right? So 2.5 squared is 6.25. 2.1 squared is 4.41. 2.01 squared is 4.0401. And 2.001 squared is 4.004001. And we can see that this limit from the right is approaching the value 4. Approaching the value 4. So good. They have a limit. Both of them have a limit. But try to notice that their limits are not the same. Here, this is approaching the value 5. Here, this is approaching the value 4. Okay, so the limit of f of x as x approaches 2 from the left. Okay, that's how we read it. If it has a, if it has an operation or a sign after that. So the limit of f of x as x approaches 2 from the left, if it's minus, is equal to 5. The limit of f of x as x approaches 2 from the right is 4. So therefore, if this things happens wherein the limits are not the same, we can say that the limit does not exist. Okay, I hope we're clear with that. Again, if the limit, if the two sided limits from the left and from the right are not the same, meaning the limit does not exist. Some books just use the D and E. Okay, D and E does not exist. Okay, that's it. I think that's the end of our video for today. What have we learned? We have learned about the concept of the limit, that the limit is not the limit of f of x as x approaches a is not the same as substitution f of a. Okay, and then we have learned about one-sided limits. Okay, we're going to read this as the limit of f of x as x approaches a from the left must be equal to the limit of f of x as x approaches a from the right. If they are equal, meaning the limit exists. The limit of this f of x exists. Okay, so therefore, the limit of f of x as x approaches a exists. But if they are not equal, therefore the limit does not exist. Okay, so with this video, I hope you had a clearer view of how to do the limit of a function. This is a fairly short video, but I hope it helps. I hope it helps. Okay, so thank you very much for watching. Um, I'll be making more of this calculus videos, so don't forget to like and subscribe. And yes, I bet I'll see you soon. Thank you very much. Okay, goodbye.